I'm going to present exploring the behavior of bistable energy harvesting via global sensitivity analysis. I'm João Pedro. I'm a master's student in mechanical engineering at São Paulo State University, Brazil. Americo is my advisor, Samuel and Paulo is my co-advisor. It's well known that bistable energy harvesting, a nonlinear system, is a great system to convert kinetic energy into electricity. However, it has different behavior has changed the parameters, become a high sensitivity system. Here we can see two videos and visualize different dynamics behaviors. Just change one parameters. In the left, we have a periodic behavior. In the right, of course, a chaotic behavior. And in a real conditions, which you need to take in account uncertain errors in a manufacturing process and environmental conditions, that we have geometry, properties of materials, and even external condition has a stochastic variables. Then a great questions arise. What happens with these uncertain parameters in our power harvesting since the system has high sensitivities? Then our objective here is identify and classify the most important parameters of bistable energy harvesting cover different dynamics behaviors. Global sensitivity analysis is a powerful tool in statistics, minded to deal with systems by stochastic point of view. The basic idea here is we input the system model and the random parameters associated and obtain as a product the most important parameter that the most affect our power harvesting. Using the Sobel index that compute a conditional variance by individual or joint effect parameters in relation to total variance. Then we can conclude, we simplify our probability model because we just consider a parameters with most effect, will help us in decision making, provide non-trivial insight into behavior since we lead to complex dynamic system, and a work tool to robustness and optimization design. The global sensitivity analysis by bistable energy harvest can be seen here. We have our schematic illustration in the left, and in the top we have the equation of motion. The results, we classify the most important parameters, basically has bigger bar, more affected by the parameters. Here we calculate for different amplitudes of excitations for exploring several scenarios of behaviors. We see that the frequency and excitation parameters, blue and green bar, has the most influence for low excitation conditions, where occur behaviors change. On the other hand, for high excitation, the piezoelectric coupling by electron equation has the most influence, that's the red bar. Then we can conclude that the damping has no effect by one third, and the most influence parameters depends on dynamic stability and behaviors. In summary, the amplitude and frequency of excitation and electromechanical coupling have the most important parameters. Thank you very much.